Good morning to everyone. I am Dr. Rajini Samuel from Sri Sathya Sai Medical College and Research Institute, Chennai, India. First of all, I thank the MAGNUS Group for giving me this opportunity to present my research findings in this International Heart Congress 2023. Cardiac duct theory, a paradigm shift in ECG interpretation or a perspective rethinking in ECG translation from scalar to vector form. Electrocardiogram is one of the oldest and most important diagnostic tool for the diagnosis of coronary artery disease, yet the basic physics principle of ECG is not clearly understood and its interpretation remains a complex task. The pattern memorization method is commonly used to analyze the ECG waves, but it is very difficult to memorize various patterns of ECG waves. So ECG interpretation remains an arduous task and ECG phobia develops in some of the junior doctors and staff nurses. The concept of cardiac duct describing the electrical activity of the heart and the equivalent triangle model with heart at the center of the homogeneous volume spherical conductor was first described by Einthoven even before a century, but he never published a complete detailed description of the same. The basic principles of vector concepts are not frequently taught and applied in ECG interpretation. The biatrial and biventricular chambers are the two electrophysiological chambers separated by an electrically inert fibrous atrioventricular ring. The electrical impulses from the SCA node spreads and activates the atrial chamber longitudinally. Each fiber activates the adjacent fibers and eventually reaches the AV node. After a delay at the AV node, supraventricular impulse is transmitted by specialized conduction system very rapidly to the ventricles. Activation of ventricles begins in left subendocardial region of the lower third of the interventricular septum, spreading transversely, followed by activation of the free walls of both ventricles transversely from the endocardium to the epicardium of the heart. The magnitude and direction of an ECG reflection is expressed in relation to a baseline referred to as the isoelectric line. TP segment, PR segment, and ST segment are the portions of the isoelectric interval lines. Atrial activation is reflected by the P wave. QRS complex represents ventricular depolarization and T wave represents ventricular repolarization. The junction between QRS complex and XT segment is the J point. The normal ST segment leaves the baseline in the isoelectric period and merges smoothly with the proximal limb of the T wave. T wave is longer in duration than the QRS complex because conduction of the repolarization wave does not utilize the higher velocity bundle branch and Purkinje system, and it depends on cell-to-cell conduction. The direction of the repolarization wave is opposite to depolarization wave, but in normal ECG, the T waves and QRS waves are similarly directed because last cells to depolarize in the ventricles are the first to repolarize. The depolarization of subepicardial cells occur after subendocardial repolarization, but repolarization of subepicardial cells occur before the subendocardial cells. The standard ECG consists of three different sets of leads. The bipolar leads 1, 2, 3, unipolar AVR, AVL and AVF leads recorded through the Goldberger's center terminal, and unipolar precordial V1 to V6 leads recorded through the stable Wilson center terminal. An electrode placed on the right leg acts as the ground for all leads, which serves as a reference electrode for recording. The augmentation is 3 by 2 or 50% higher for leads recorded through GCT compared with leads recorded through WCT. Correction factor 1.154 is used to correct for the difference in strength, the resistance between the bipolar and unipolar limb leads. In the x-axis reference system, the center point is a 0 point that denotes the origin. If a perpendicular line is drawn from the tip of the cardiac vector into the respective leads, then the corresponding segment in that leads represents the magnitude of the voltage recorded in that lead. Lead 1 plus lead 3 is equal to lead 2 is the Einthoven equation. The bipolar and unipolar limb leads are related using these equations. Determination in ECG, voltage recorded in a particular lead in ECG is due to the projection of heart vector and lead vector. Angle can be determined using the voltage recorded in AVF and lead 1. So tan alpha is AVF divided by lead 1, but the correction factor 1.154 is used to correct for the difference in strength or resistance between the bipolar and unipolar limb leads. The formula is tan alpha is equal to 1.154 into AVF divided by lead 1. Vector quantities are useful in describing the motion and the position of a particle that is moving in a plane. Vector has both magnitude and direction, but scalar has only magnitude and no direction. Position vector is defined as a vector that indicates either the position or the location of any given point with respect to any reference point. The position vectors represent the location of a moving point. As the point moves, the position vector changes in magnitude and direction. Displacement vector is the change in position vector. It is defined as a vector joining its initial position to its final position, whose length the shortest distance between the initial and final point. So displacement is equal to velocity into time taken, and distance is equal, which is similar to distance is equal to speed into time taken. Displacement and velocity are vectors. Distance, speed, and time are scalar quantities. So in the right angle triangle, the side opposite 90 degrees is hypotenuse. So these are the known trigonometric relations. Sin theta is equal to opposite side divided by hypotenuse. Cos theta is equal to adjacent side divided by hypotenuse. Tan theta is sin theta divided by cos theta. So tan theta is equal to opposite side divided by adjacent side. A unit vector is a vector quantity whose magnitude is 1 and has direction only. The unit vector has no unit and it is a dimensionless quantity. So vector is equal to vector's magnitude into unit vector. Suppose OL is a vector. OL vector is equal to OL magnitude into OL unit vector. Lead vector concept. Lead vector OL vector that denotes the orientation of the electrode also has magnitude or strength, but it can be compared relatively with other lead vectors. So the magnitude or strength of the bipolar limb leads and the unipolar limb leads can be compared using the correction factor 1.154. Similarly, the unipolar limb leads and unipolar precordial lead strength can be compared using the augmentation factor. So lead vector OL vector is equal to OL magnitude into OL unit vector. So this OL unit vector has no unit and it denotes direction only, but the OL vector has unit measured in meter. Suppose the magnitude of the vector is taken as 1, then lead vector is equal to 1 into unit vector. So lead vector is a unit vector multiplied by magnitude of 1, and so this is measured in meter. So projection of hot vector on lead vector. If the two vectors are multiplied and the product is a scalar quantity, then it is called scalar or dot product. It is equal to the product of the magnitude of the two vectors and the cosine of the smallest angle between them. So this is OHV is a right angle triangle. A perpendicular line is drawn from the point H, tip of the hot vector, that meets at point B on lead vector. So OV denotes the voltage recorded in that particular lead. So using the trigonometric relations, cos alpha is equal to OV divided by OH. So OV is equal to OH cos alpha. That denotes the voltage recorded in that particular lead. So applying the dot product, so OH dot OL is equal to OH into OL cos alpha. So OH denotes the magnitude of the hot vector, OL denotes the magnitude of the lead vector. If the magnitude of the lead vector is taken as 1, then OL is equal to 1 into OL unit vector. So if you substitute, we will be getting H dot L is equal to OH cos alpha. So H dot L is equal to OH cos alpha is the cardiac vector hypothesis. So cardiac vector hypothesis states that voltage recorded in a particular lead is a result of dot product between lead vector and cardiac vector. So cardiac vector is measured in volt per meter and lead vector is measured in meter. So the result is voltage. Voltage is measured in volt. That is a scalar quantity. So cardiac hypothesis states that voltage recorded in a particular lead is a result of dot product between cardiac vector and lead vector. So voltage recorded in a particular lead depends on both the magnitude and direction of the cardiac vector, but only on the direction of the lead vector. So cardiac vector is an electrical field vector of dimension volt per meter. Lead vector in meter denotes the orientation of the electrode position only, but the relative strength of the various leads can be compared and applied using the correction factors in the cardiac vector theory. So the cardiac vector theory is very helpful to understand the concept of ECG. The magnitude and orientation of the hot vector with lead vector electrode orientation will cause deflections in the ECG voltage in the y-axis, vertical axis, resulting in the formation of ECG waves. If the magnitude of P, QRST and ST vector is high, the voltage recorded will be high, and vice versa. So in the tabular column, the cos theta values are given. The voltage recorded will be positive if both the vectors are in the same direction, and negative if both the vectors are moving in opposite direction, because cos value is negative for obtuse angle. As the angle between cardiac and lead vector increases, the voltage recorded in the particular lead will decrease, and vice versa. This is clearly seen from the tabular column, from the cos values. If the cardiac vector is parallel to a particular lead, ECG will record maximum deflection on that lead, because cos 0 is 1. Similarly, if the cardiac vector is perpendicular 90 degree, then the net intrusion on the lead will be either equiphasic or null deflection, because cos 90 is 0. So application of cardiac hypothesis, the unipolar lead AVR will be usually negative because the heart vector is moving away from the electrode placed. The normal resultant heart vector is usually parallel to lead 2, and so it is used as a rhythm strip continuously recorded for 10 seconds to determine the heart rate and rhythm. So no ECG deflections are recorded in cardiac arrest or CA system because the magnitude of vector is 0. Technical errors, the reversal of the leads and the misplacement of the leads are the common but underreported technical error which can hinder proper ECG interpretation. For example, the lead is reversed, direction of the lead is opposite. So the voltage will be recorded wrongly and the deflection will also change. Similarly, the precordial leads are not placed in correct position. The magnitude and direction of the heart vector will be different, and the voltage recorded will be a false value, which sometimes mimic pathologies, leading to misdiagnosis. Displacement vector of ECG. Velocity of the cardiac vector is related with time in the x-axis of ECG. The ECG intervals will be prolonged if the cardiac vector velocity is lower or the distance traveled by the vector is increased. Example, any enlargement or thickness. If the ECG interval will be shortened if the cardiac vector velocity is increased or the distance traveled with the vector is shortened. Example, any bypass route or accessory path. Displacement vector gives information about the change in position, distance and the direction that's traveled from its initial to final position for each wave or segment. If the magnitude of the displacement vector is high, the conduction velocity of the cardiac vector is lower, so more time is needed, and vice versa. So wider waves are longer duration, narrow waves are shorter duration. The formation of each ECG waves are represented by one or multiple position vectors that denote the location of a moving point. As the point moves due to the electrical activity of the heart, the position vector changes in magnitude and direction. The displacement of ST segment, either elevation or depression, with reference to the isolated line, is clinically the most important part of ECG. The displacement vector denotes the difference between the initial J point and the final point that merges with the T wave. So ST segment is an isolated period in ECG. When the myocardium of the heart is injured, it results in leakage of current. This is called current of injury. The ST vector, current of injury vector, move towards the injured surface. If the leads are oriented towards the current of injury vector, it results in positive deflection. It results in ST elevation because the direction vector is from endocardium to epicardium. So some of the ST elevations are shown here. The position vectors change the shape and slope of ST segment elevations of myocardial injury. In severe ischemia, the position vectors moves and forms horizontal depression, downsloping and sagging ST segment depression by changing its shape and slope. Reciprocal ST depression, negative deflection will be seen in the leads oriented away from the current of injury vector. In sub-endocardial infarction, the ST segment and T wave changes will be negative, which is opposite a mirror image to those associated with transmural or sub-epicardial infarction. ST depression is present because the direction of the current of injury vector is from epicardial to endocardium, which is opposite to the ST elevation. P wave is formed by the longitudinal activation of the atrial chamber. The position vector from its initial point in the baseline to the apex forms the proximal limb, and the position vector from the apex to the final point in the baseline forms the distal limb. The right atrial enlargement and left atrial enlargement can be identified using the changes in these position vectors. The supraventricular impulse is transmitted very rapidly by the specialized conduction system. Delta wave is a slid upstroke in the QRS complex related to a pre-excitation of ventricles due to an extra pathway that connects atria to the ventricles. It is clearly shown in the graph. Activation of ventricles begins in left subendocardial region of the lower third of the interventricular septum, spreading transversely from left to right. It is opposed by small activation force that rises in the right subendocardial region. So the larger left to right force dominates, so the resultant vector is directed transversely from left to right through the lower third of the interventricular septum. This is called septal vector. Activation of the interventricular septum is then followed by activation of the free walls of both the ventricles. This occurs transversely from the subendocardial to the subepicardial regions of the free walls of both the ventricles. The relatively large force from right to left through the larger free wall of left ventricle occurs synchronously with the smaller opposing force directed from left to right through the smaller free wall of right ventricle. So the larger right to force dominates, so the resultant vector is directed transversely from right to left. So it is clearly shown in the diagram. So the bigger resultant vector, the smaller opposing smaller. So we have to apply these concepts, and the same cardiac vector theory can be applied for the explanation of RS complex and the transition zone capital R capital S complex, and then small q capital R complex. So same cardiac vector theory can be applied to explain the changes in the QRS complex. The multiple moment of the position and displacement vectors of this complex will change the shape and size of ECG waves in hypertrophy and bundle branch block. The cardiac vector velocity is low, the conduction time will increase, resulting in wider waves and secondary STT changes. QRS vector denotes the ventricular depolarization. So if the myocardial tissue is necrosed, it is electrically inert and does not get depolarized. This is an electrical hole. The electrodes oriented towards this will record the activation of the opposite ventricular wall. So QRS deflection will be negative. Pathological Q waves will be seen. This QRS vector will move away from the infarcted or necrosed region. The normal QRS vector is from -30 to 90. Normal T wave axis between 0 and 90. The normal QRST angle does not exceed 60 in the frontal plane. The T wave vector move away from the affected region. In interventricular conduction defect, the duration of the QRS complex is prolonged. So the T vector move away from the QRS vector due to the secondary phenomenon and do not indicate primary abnormality. During ischemia, that denotes a decreased blood flow. The muscle does not die because blood flow is sufficient to maintain life of the myocardium but not sufficient to cause repolarization. So T wave is produced by repolarization. So ischemia causes deviation of T wave axis. So T wave inversion, negative deflection results, and the T wave vector will not be in the left lower quadrant. We look at it in other quadrant. Following the fully evolved phase of acute myocardial infarction, there is a gradual resolution of abnormalities. The chronic stabilized phase, the elevated ST segment gradually returns to baseline, becoming predominantly isolated once again. The inverted T wave gradually regains its positivity. Even the QRS complex may regain some of its previous positivity. In the x-axis reference system of ECG, plot the net voltages of bipolar limb leads and connect them. Similarly, plot the net voltages of unipolar limb leads and connect them, which form equilateral triangles. So these equilateral triangles can be converted into circle. The orientation of the circle is the same for both the bipolar and unipolar limb leads because the electrode position is the same for both of them and they record same electrical field of the heart but in a different view. But the magnification is different, higher for bipolar limb leads because they have higher resistance. So this denotes the Einthoven circular triangle hypothesis. So voltage recorded by the electrodes, lead 1, 2, 3, AVR, AVL, AVF, denoting the right arm, and left leg or the vertices of an electrical equilateral triangle. The orientation of the circle is the same, but the magnification is different because bipolar and unipolar limb leads have different resistance. Each circle of same origin, same orientation, but different radii because bipolar and unipolar limb leads have different resistance. The ratio of the resistance is 4/3. The square root of 4/3 is 1.154. So multiply each unipolar limb lead voltages by the correction factor 1.154 and then plot. Now the two equilateral triangles are in the same circle. So each cardiac wave can be represented as a form of circles. The diameter of the circle denotes the cardiac vector, the resultant vector. The perimeter, circumference of the circle denotes the electrical field of the heart with the heart at the center of the circle. So thus heart is at the center of the electrical field it generates and the right arm, and left leg are the extensions of its electrical field, which was compared by Einthoven, the homogeneous volume spherical conductor with the heart in the center of the sphere. So the heart in zero potential is situated in the center of the x-axis reference system, that is the origin. This does not denote the Wilson center terminal. When the heart acquires certain potential during depolarization and repolarization, the triangle gets shifted, but the equilateral shape of the triangle remains the same in any of the four quadrants of the x-axis reference system. So each wave's cardiac waves P, QRS, T and ST can be represented in the form of circles in the x-axis reference system. All circles, the orientation diameter representing the resultant cardiac vector should be formed in the left lower quadrant except QRS, which can go up to minus 30. When the angle between QRS and T circle increases, it usually denotes ischemia. The voltage will be higher if the size of the circle is larger. ST segment is an isoelectric period, so no circle will be seen. The formation of circle and its magnitude during ST segment indicate the amount of myocardial injury. So the vector principle of cardiac hypothesis and the representation of resultant vector in the form of circle can be applied to diagnose most of the common cardiac diseases. So 4 examples I have shown here: normal QRST angle, inferior wall ischemia, inferior wall MI, and intraventricular conduction defect. The first example, QRS and T circles are constructed for the normal QRST angle. So values are taken from this graph, and these are derived using the already well-known Einthoven equation on the relation between unipolar and bipolar limb leads. You can apply the same cardiac hypothesis also. The second one, T wave inversion seen in lead 3 and AVF. So T wave vector is moving away from the inferior wall. So T wave vector is not in the left lower quadrant. It has shifted. In ischemia, T vector move away from the affected wall. Primary change. The third example, ST elevation seen in leads 2, 3 and AVF, denoting inferior wall MI. So ST vector is towards the injured surface. And reciprocal ST depression is seen in the leads orient away from the current of injury. QRS vector is not deviated because inferior wall is not infarcted, it is injured. The fourth example, intraventricular conduction defect, the QRS and T, they are moving away. They are in opposite direction. So abnormal QRS T angle. So T vector is moving away due to secondary changes, and this does not denote the primary change. So conclusion, ECG plays a major role in the diagnosis of coronary artery disease, which is the #1 killer disease of the world. Cardiac hypothesis and Einthoven's equilateral triangle hypothesis forms the basic foundation in the teaching of electrocardiogram. The better understanding of the vector physics principle of ECG helps to clearly analyze the size and shape of the ECG waves to correlate in various cardiac diseases. That helps to overcome the arduous task of pattern memorization method of ECG interpretation. So the combination of the 12 lead ECG with this resultant cardiac vector represented by circle provide the optimum approach to ECG interpretation, resulting in saving millions of lives of cardiac patients. So I thank one and all for giving me this opportunity to present my research findings in this international conference. Thank you. And these are my references.